And what optical density is the overall darkening of the image. So if you have an image that is very dark, then we refer to that as being very dense. So you think about a chest x-ray and the difference in the density levels on a chest x-ray. Like the lungs are gonna be very dark, that's dense. The bones, on the other hand, show up very light, and that's a lack of density. So the darker something is, the more dense it is. And optical density and radiographic density are the same thing. Optical density and patient density are pretty much inversely proportional. So a high patient density bone is going to give you a low optical density. Okay?
The generators, like the single phase, three phase things?
Yes, you remember talking about the voltage waveform, and what we have supplied to us is alternating current in a single phase. And what we do with it is we rectify it, and then we invert the negative side. So it's still single phase, but it's single phase direct current, right? And then three phase, what we do is we come along and we overlap 3 voltage waveforms. So I just drew 3, but there's really 6 in between each one of those. So that would be 3 phase, right? And then high frequency is where basically what we do is we kind of cut the tops off of each one of those so that we make almost a consistent voltage waveform like that. So what we get as, and we're going to talk a little bit about that here in a bit, but what we get is a higher output from a 3-phase or high frequency machine than what we do with a single phase machine. We get a higher average, we get a higher output, we get a better quality x-ray beam. And what we're going to talk about next semester, what we're going to talk about today is kind of a summation of Trina's class in imaging, and it's an intro into what we're going to do next semester. And if you can, just spend some time over the Christmas break thinking about what we're going to talk about today, it's going to make, and trying to understand what we're going to talk about today, it's going to make next semester a little bit easier. So there is a difference also, just like the difference between patient density and radiographic density, there's a difference between beam quality and radiographic quality. Radiographic quality is the quality of the image that we see, and it's affected by the x-ray beam and the quality of the x-ray beam. So we have high quality x-ray beam, meaning we have a lot of high energy x-ray photons. But what do you know about high energy x-ray photons?
They create a lot of scatter.
What's that?
They create a lot of scatter.
They create a lot of scatter, right? So if they create a lot of scatter, what does that do to your image? What do we not want on the image?
Fog.
Fog, which is
Yeah,
scattered, right? So the higher the beam quality, unfortunately, the lower the image quality. Okay. So and the reason I went there with all that is because in beam quality, every time this thing drops down to this point right here, you're at 0 kVp. So as we increase the number of pulses, do we ever drop to 0 kVp? No, which means we get a higher average energy, which is a better quality x-ray beam, but it's going to give us a worse image. Okay, so 3-phase means higher output, higher average, better quality x-ray beam, lower quality image resulting from it. Okay. What else?
Reciprocity.
Reciprocity means give and take. So if you're looking at 100 MA times 1 second exposure, what's your mass?
100.
100, right, 100 mass. If I have 200 MA times 1/2 second exposure, what's our mass?
100.
100 mass. Should our output be the same? 100 means 100, it should be, in a perfect world, it should be identical. What we're going to learn next semester is there's some variances between MA stations and timer. They can be somewhat off, so there's going to be, they may not be exactly, so somewhere around the same. But reciprocity means that 100 mass should be 100 mass regardless of how you arrive at that 100. So 400 and a quarter second gives you 100. Yeah, there you go. So it should all mean the same thing. That's reciprocity.
X-ray distribution curve
That's what we're talking about today.
and the step wedge.
Step wedge. The step wedge, the step wedge is what we used to use to determine the characteristics of X-ray beam, the output of X-ray beam, both MA in time, so mass, and KVP. And we used to use it in quality control. And really, that's probably something that needs to come out of the review. I don't think it's on the final. But what it does is we can measure the characteristics of the X-ray beam if we expose a step wedge is just a chunk of aluminum that goes up. It's a wedge shape, but it goes up kind of like stair steps. So if we make an exposure, and we'll talk a little bit about this today, if we make an exposure and let's say we use 50 kVp and we only penetrate through that step right there, all right, then that tells us that the penetrability of that X-ray beam is only through that particular step. Now, if we take an X-ray on that same machine tomorrow and it penetrates through that step, what do you think that tells us? What controls your penetration? KVP, right. So either our machine was off yesterday when it only penetrated that one, or more likely our machine is not shooting right because it penetrated through a thick chunk of step wedge. That's also what we call a penetrometer because it, measures the penetration. Penetrometer is also shown. Sensitometer is what we use to measure how much, relative density is on each one of those.
As far as like math, is all of the like formulas that are written out in this?
Yes, yeah, and here's a sneaky secret. If you know, and this goes all the way through to the registry, if you really know how the formulas work, chances are, even on the registry, out of 200 questions, you might have to actually put a calculator to 2 tops. If you really know how the formulas work and why they work that way, like, let's say inverse square law. What is inverse square law?
Intensity is inversely related to
distance, but it's the square of the distance, right? So, if you increase your distance, what happens to your intensity?
decrease.
It decreases, right? So by a square of the distance. So if you double your distance, then your intensity decreases by a factor of 4, right? If you go from 40 to 72 inches, that conversion is a factor of 3.24, right? So, on most of your test questions, again, all the way through the registry, what you're probably gonna see are these. You're gonna see one that's just so ridiculous that you just should ignore it, right? You're gonna see one that the math works out if you invert the problem, which means that you're talking about the inverse square law, so you increase the distance and your intensity should decrease by a factor of the square of the distance, right? So if you double your distance, then you should have 1/4 of the intensity. So what you'll see is one answer that will go in the opposite direction. You double your distance and your intensity increases by a factor of 4. So if you don't know how the formula works, then that one might trip you up. And then you might have another one that is close, right? You increase your distance and your intensity decreases by a factor of 2. So really, if you're paying attention to the question and the answers and you know how the formula works, you can pick out the answer, the appropriate answer, without ever having to do the math. If it doubles, then you know that's wrong. If it quadruples, then you know that's wrong. If it decreases by a factor of 2, you know that's wrong. If it decreases by a factor of 4, when you increase your distance by a factor of 2, there's your right answer. Does that kind of make sense? So, I mean, all the way through the registry, it's, if you're looking at things like focal spot blur, yeah, you're gonna have to put a pencil in that. But inverse square law, direct square law, things like that, you should be able to pick out the right answer just by looking at the question and the answers. If you understand the equation and why it happens the way it happens. What?
Is there a difference between failed exposure and the ready light failure? 'Cause it's kind of the same.
I'm sorry?
The ready light failure and failed exposure.
Ready light means that you're not gonna get any kind of an exposure. Let me see exactly how it's worded. So, ready light failure could be, but yeah, what was the other one? Failed exposure, no exposure. Could we do the, yeah, same thing. Yeah. What? Is it? All right. Well, then today, what we're gonna talk about are really 3 different things. We're gonna talk about creation of X-rays, which we've talked about since the opening lecture. We're gonna talk about the emission, which is really what you use as your usable X-ray beam. And then we're gonna talk about the factors that affect both of those. And that is in beam quality and quantity. And the measure of quality. So, when we're talking about X-ray creation, we're talking about the brims and the characteristic X-rays as they're created at the target. And there's a significant difference between creation and emission. Okay, so at creation, what we have is every X-ray beam that's created. But we've talked enough about the construction of the X-ray tube and of the housing and the things inside of the housing to know that what's created is not what's emitted from collimator housing, right? And collimator housing is where we're gonna have our useful beam emitted from. So the rest of the X-ray beam that's created should be absorbed inside of the protective housing. That's the purpose for the protective housing. So the only thing that we have is what is escaping through the window in the useful beam. But even what comes through that window is not going to be representative of what came directly off of the target itself. So the creation of X-rays is all about loss of kinetic energy, and we talked about the different ways that we create X-rays. So we've got 2. We've got one that is caused by the loss of kinetic energy just as it goes close to the nucleus of the atom. It may even run into the nucleus of the atom. And the other by ejection of electrons and replacement of the electrons that it ejects. So we're going to start with brims. All right, so going all the way back to the atomic structure, what did we say is the most of the area inside of an atom is? Empty space, right. So fundamentally what we've got in the atomic structure is we've got protons, neutrons, electrons, and protons and neutrons have most of the weight, right? They have most of the weight, most of the size, but still inside the structure of the atom, most of the area is empty, right? And we gave the protons and the neutrons an effective atomic mass unit of 1, right? Or atomic mass of 1. And the electrons were so small, we gave them a 0, right? So on the scale of, just the numerical scale, 1 is pretty low, right? Zero is non-existent. So fundamentally what we're doing is we've got a collection of protons and neutrons, but they amount to almost nothing, right? As a matter of fact, they're so small we can't see. And then what we're gonna do is, and then we've got electrons floating around that, and those are so small that we just almost don't even recognize them, right? So we've got 2 here, we've got a number out here, and so on and so forth. So what we're gonna do is we're gonna take, relatively speaking, this great big fat filament. This is on the atomic level. So the filament is massive compared to individual atom size, right? But we're gonna take this thing, we're gonna line up all these electrons on it. So we've got all these electrons, and we're gonna send them across the X-ray tube. And as they travel across the X-ray tube, they're gonna try to spread out. We're gonna have means of controlling that, but they're gonna try to spread out. But if we line all these things up, and we've got these atoms over here, and they just follow in the path that they are lined up against these atoms, what's the likelihood that any one of these is going to get close, even if they come straight across? How many of them are going to pass really close to the nucleus of the atom?
Very little.
Very little, almost none, right? Almost none. So most of them are going to be way out here. So what did we talk? What did we say about the attraction between the nucleus and the projectile electrons?
The closer you are to the nucleus, the higher binding energy you have, and vice versa.
Okay, you're talking about these right here.
Okay.
Okay, so these electrons, yes, yeah, we'll get there in a minute. But we said that the nucleus is going to act kind of like a gravitational pull, and what we've got is basically a comet coming through our solar system here, right? So if it gets too close to the sun, what does it do? It falls into the sun, right? But most of the time that doesn't happen. The comet, like Halley's Comet, comes through every, I think it's 78 years, and has for centuries, and it hadn't fallen into the sun, right? Because it doesn't get close enough to the nucleus of the atom. Likewise, these electrons get close enough to the nucleus of the atom, and the nucleus is going to grab it and it's going to send it off in a different direction. And what we're going to have is a loss of kinetic energy. So if this thing comes in with 100 kVp worth of energy, and it slows significantly, and we've talked about that in physics. If we've got something that you're driving down the road, you whip the wheel, then you're going to increase your resistance on the road. You're going to lose some speed, right? Same thing happens here. It leaves with less energy than what it came in with. So if it got really close to the nucleus of the atom and it lost 99 kVp worth of energy, it left with 1 kVp worth of energy because it lost 99 kVp worth of energy, then we're going to create an X-ray photon in the energy that is the difference between incoming and outgoing. So mathematically, what is difference? What's that? Subtraction, right. So 100 minus 1 is
99.
99. Right, so we got an X-ray photon in 99 kVp range. But most of them pass way out here, so the attraction, again, like a comet, like Halley's Comet, it goes off maybe in a different direction. Is it going to lose some kinetic energy? Yes, absolutely. It also came in with 99 kVp or 100 kVp, but it might have left with 99 kVp. So what is it going to pick off an X-ray photon? Yes. What's the energy of that X-ray photon? 1, right. So this is 1 kVp. Okay, so considering the size of the nucleus being so small we can't see it, and the size of the electron being so small we don't even give it a weight. So we're shooting something that almost doesn't exist as something we can't see. So the likelihood of these happening is very low, right? So most of your X-ray photons are going to be these things out here. Very few high energy X-ray photons. So the further out they go, the less they have. They're still gonna create X-ray photons all the way out. But the ones that create the highest energy X-ray photons are gonna be the ones closest to the nucleus of the atom. Okay? Now, how that manifests itself is on what we call a BREM spectrum, an emission spectrum. Okay? What we have at the point of X-ray creation, and Bushong's going to run through actual emission. I'm going to explain emission a little bit deeper. At the point of creation, inside of the X-ray tube, on the target itself, because of all this, most of the X-ray photons that we create are very low energy photons. So most of what we create is heat. 99% of it is heat. But most of the actual X-ray photons that are created are going to be low energy X-ray photons. So if we plotted them on a 2-axis graph, and we said that this was the energy of the X-ray beam measured in kVp, and this was the number of X-ray photons that we create, most of the photons are going to be low. This is going to be both zero number and zero energy. Most of our X-ray photons are going to be low energy, high numbers. You get that? Because we're shooting something so small it almost doesn't exist. It's something so small that we can't see it. It ain't going to get close to it, most likely, right? Most of them are going to be these low energy X-ray photons. So most of what we create, not emit, but create, are going to be low energy. We're going to have a lot of low energy X-ray photons. You with me? All right. So if we plotted that, what we would have is, in comparison, our high energy X-ray photons, how many were we going to have? Not many, right? So numbers on high energy, very low. Numbers on low energy are going to be very high. So at the point of creation, X-ray creation, that's what we're going to see. Okay? Our plot or our graph is going to show that we've got a tremendous number of low energy X-ray photons, almost no high energy X-ray photons. So if we said that this was a 100 kVp, if we set 100 kVp on our control panel, then our peak energy way out here should be 100 kVp. Our minimum energy, what's it going to be?
1.
Whatever, 0.0000 something even, you know. Still going to be X-rays, but they're going to be extremely low energy X-ray photons. All right? Is that the X-ray beam we use, though? I mean, do you just have an anode in your room and you're shooting electrons at it? No. What's it got to go through to get to your patient? Glass, oil, port, the housing, mirror, right? At least that, all the way up to the point of where you have 2.5 millimeters of aluminum equivalent, right? Is that going to stay the same through the life of the X-ray tube?
No.
No. Why? Tanning. I learned something this semester, didn't you? Tanning. So that's going to increase that over the life of the X-ray tube, right? But when your X-ray tube is brand new, it should have at least 2.5 millimeters of aluminum equivalent to it. What is the purpose? What was the original purpose for filtration?
To get rid of low energy photons.
Get rid of low energy X-ray photons. Why did we want to get rid of low energy X-ray photons?
They have less penetrability.
They have no penetrability. They're not going to get through the patient. So that all they do is add dose to the patient, right? So we want to get rid of those. That's what this is all about. That's the only reason for this, is to get rid of low energy X-ray photons so that you don't overdose the patient and give them a high, what we call, and what you'll learn about next semester, is entrance skin exposure. Entrance skin exposure is just that. It's what is going to be deposited inside of the patient's body and the difference between what goes through the patient and what just absorbs inside of the patient. So our aluminum, our 2.5 millimeters of aluminum equivalent, is our filtration, minimum filtration to a usable diagnostic X-ray tube. So what happens is that as the X-ray beam that's created, this is created X-ray beam, goes through the glass, We said that all material is radiolucent, meaning that, what? What's that? You filter some out, right? There's some selective absorption. Glass absorbs X-rays. Just not a whole lot of them. But what controls your penetration? KVP, right? So down here we've got high KVP or low KVP?
We have
Huh?
high,
Down here, this,
low.
so this is low KVP, right? So if high KVP controls your penetration, mostly, then low KVP is very penetrating, not very penetrating. Not very penetrating. So when we're talking about glass, which has a low, for our usable X-ray beam, a low amount of radiopacity, is radiolucent, but it absorbs some X-rays, just very low energy X-ray photons, then we can say that what's going to be affected by the glass is not so much this down here, but this up here, right? So what we get is the glass is going to take some of that stuff out. Now, what happened as we took some of that out? What's that?
The numbers went down.
Bingo. Numbers. So with aluminum, we got, with filtration, with the glass, we got a decrease in numbers. Okay, what else happened? Which ones did we lose? The low energy photons. So which ones did we keep? High energy photons, right? So if I throw out your lowest test grade, how would that affect you?
Bring the grade up.
Bring your grade up, and what do we call that grade? Your average, right? So if we throw out all these low energy X-ray photons and we're left with higher energy photons, what would that do to the average beam energy? Increases average. So what we did was we lost the numbers, but what we were left with were the higher energy, more likely to penetrate X-ray photons. Okay? So that's emission from the X-ray tube. Is that what you use? Is that what you expose your patient to? No, it's still got to go through the next step is the oil. Oil is, what are you made of? This is going to get kind of graphic and kind of disgusting. But you brown hamburger meat, right? What do you get? Grease, right? You think you got grease? Yeah, grease is nothing but oil, right? Right? Do you absorb X-rays? If you didn't, then these would be useless to us, right? So does the oil absorb X-rays? Absolutely. Absolutely. So it's going to take out more of them. So now our distribution curve looks more like that without the big gap. Okay? So what happened as it went through the oil? Lost more numbers, but what we were left with is a higher average. Now throughout the bottom two test grades. Now what does it go through? The port, the window, right? Something's got to hold that oil in. It's probably made of metal, some sort of thin metal. Metal absorb X-rays. Who has made an exposure without pulling a patient's pants down if they're wearing jeans? Somebody is lying. Somebody in this room besides me has done it, right? You can see the snap, you can see the zippers, it's all there, right? So metal absorbs X-rays. So now going through that port, our distribution curve looks like that. So what happened? We lost more numbers, the average increased. We're becoming safer for the patient. Now what does it go through? Do you see the light bulb? If you look up in your collimator housing, do you see the light bulb?
Mirror.
Mirror. What's a mirror made out of?
Glass.
Glass and something to make it shiny or reflective, right? Maybe a metal there too. So what's that gonna do?
Lower your numbers.
decrease the numbers, increase the average. So that our distribution curve, once it comes out of the housing, now this is truly our emission curve, looks like this. Okay? So what we can look at in this is we've got, difference in KVP, our peak energy, it tells us what our peak energy is, tells us what our minimum energy is, and minimum energy should never be zero. It tells us about what our average is. And our average is usually about 1/3 of the peak. So in this X-ray beam that we've created here, our average beam energy is roughly 33 kVp, right? So if I added more filtration, what's gonna happen? If I go above the 2.5 millimeters of aluminum, what's gonna happen?
You get even more.
Keep doing this same thing. We're gonna decrease numbers and increase average. So how we determine average is where this is. So if we continue to decrease or increase our filtration, what's gonna happen is that average, we lose more on the low end, and what we're left with is more on the high end. If that tells us what our average is, what happened to our average right there? Now the numbers went down. This represents numbers over here. I'm sorry. The position of the highest part of that bubble represents the average.
So it moved more to the right.
So it moved more to the right, which is towards the
The higher.
high energy side, right? So with increased filtration, we remove numbers, we increase the average, we determine the numbers by the area under what we call the brims or the brims distribution spectrum. Now, the brim spectrum is what we call a continuous spectrum. I say continuous, what does that mean? Goes on forever, right? It doesn't stop. It is consistently flowing. It just goes on and on and on. So the brim spectrum represents all energy levels from the very peak energy down to the minimum, the smallest energy. All right? So the brim spectrum. There we go. All right, everybody good with this so far? Okay. Then I'm going to erase this, and we're going to talk about the different things, and this is really kind of bleeding into chapter 8, different things that affect that brim spectrum. So far, we've had one example, and that is filtration. Okay, but we also need to talk about KVP. So looking at this brim spectrum, if I decrease my KVP, what's going to happen? Wow, it shows up there in the bottom. What's going to happen? Okay. And by big, what do you mean? Okay, so this is 100 kVp there. What if I lower it to 80? Where is that going to intersect? That way, right. So it's going to be down here. So what's going to happen, I'm going to get rid of this, is that it's going to fairly well mirror our minimum energy is going to remain the same, because what affects minimum energy? There's only one thing that affects minimum energy.
Mass. Oh, KVP. Filtration.
Filtration. Okay. I get my thumb pointed in the right direction. Filtration. The only thing that affects your minimum energy is filtration. The less filtration you have, the lower your minimum energy. The more filtration you have, the higher your minimum energy. All right, so the only thing that affects filtration is the minimum energy is filtration. So it affects minimum, it affects average, and it affects numbers. So what I lost whenever I went to 80 kVp, this is 80 kVp, is I lost peak energy, right? I went from 100 to 80 because I lowered my kVp. So in lowering my kVp, let's say now we we went the other direction with that. I didn't throw out your minimum test grade, I threw out your maximum test grade.
I will do that.
So now what happens? What happens to your average is it goes down, right? So KVP also affects your average. It is the only thing that affects your peak energy. And what do we say that this area under here represented? Numbers, right. So it affects numbers as well, right? Okay. I'm gonna expand the view on this. So where we are right now is 100 kVp and 80 kVp, right? So here's your average, ish, right? So filtration, minimum, average, it's the only thing that affects minimum. It affects your average and it decreases your numbers. So we've got decrease in numbers, increase average, and increases not the number of minimum X-ray photons, but it increases the energy of the minimum X-ray photons, okay? So KVP affects the peak, so it changes the peak, it changes the average, and it changes the numbers. What we also have is mass, all right? What are the words that mass represents? Amp, right? So what is the amp?
The number.
The number.
Just a measure of electrons, right? So it's just a measure of electrons. So if we change our mass, then what we're changing is the number of electrons we have available on the filament. That changes the number of electrons we send across the tube. That changes the number of X-rays that we create, each one of those proportionally. You double your mass, you double the electrons, you double the electrons you send, you double the number of photons you create. So in those, what happens to your peak energy? This is V. Okay, so let's do this. Let's label them. Change KVP. Also going to do this and say this was filtration. And now we're going to have mass. So if I change my mass, I already said that there's only one thing that affects the minimum energy of your X-ray beam, and that is filtration. I already said that there's only one thing that affects the maximum, and that is KVP, right? So we already said that if you change your mass, you just change the number of electrons you send and directly change the number of photons you create. So really, when you change your mass, your minimum is going to come off at the same spot. And you should have a distribution curve that does nothing but change the numbers. Okay? So what does mass change?
Numbers.
Numbers only. Only thing it changes numbers. No effect on peak energy, no effect on average, just affects the numbers. Only thing it affects. Okay? We've got voltage waveform. All right, so we were talking about voltage waveform before, and what did I say that voltage waveform, when we go from single phase to three phase, that never happens?
Minimum energy.
What's that?
The minimum energy never goes back down to zero.
Never goes back down to zero. Right, so what we're talking about here is the voltage waveform. So in all this stuff that we've already talked about, what seems most similar between voltage waveform and what we've already talked about? Filtration? Just the words. That's all I'm looking for, just the words. Filtration, sound like voltage waveform? Mass sound like voltage waveform? Kilovoltage sound like voltage waveform? Okay, all right. So, But this comes with a caveat. I already said that the only thing that affects peak energy is filtration. Or, no, peak energy is kVp. Filtration is minimum energy. Okay? So if voltage waveform, we're dealing with voltage here, and difference in voltage never drops to zero. It never ever drops to zero with three-phase or high frequency. Then what's going to happen to your average if you never go to zero? On a single phase you do, but on three phase you don't. Again, you're throwing out the minimum, so you got
A
higher average, right? But what happens to your peak? Nothing, because the only thing that affects peak energy is kVp. What happens to your minimum? Because the only thing that affects minimum energy is filtration, right? So, as you change your voltage waveform from single phase to three phase, that's 31 phase, three phase, then what you're going to have is an increase in average and an increase in numbers. Okay? So it's going to look a lot like mass, only with mass, you just went straight up. With voltage waveform, kind of running out of room to come off of this with voltage waveform, it goes up. And let's go back to the 80 kVp. It goes up, but your average increases too. You see that? So from three phase to high frequency, or from single phase to three phase, or from single phase to high frequency, what you get is an increase in average, you get an increase in output, so the brim spectrum goes up. You get an increase in average, increase in output with increase in phases from single phase to three phase. And really the only other thing that could affect your brim spectrum is the type of target material. And instead of drawing that, I'm going to just draw your attention to page 132. Okay. So on page 132, they show a hypothetical of what would happen to your brim's distribution spectrum if you had different target material. If you used, instead of tungsten, you use gold. And gold has a higher atomic number than tungsten. So what do you know about atomic number? If you have one thing that has an atomic number of 2, comparing it to something with an atomic number of 4, what do you have more of? Protons. Protons, probably neutrons, you have a bigger nucleus. So if you have a bigger nucleus, it's basically like you got a bigger sun, right? So now let's reintroduce Halley's Comet. If suddenly our sun was twice as big as what it is now, and we had all this stuff buzzing around it at the same rate of speed, so you have the same centripetal force and centrifugal force as what we have right now, but our sun gets bigger, what happens? We're going to fall in, right? We're going to fall in. So if we use that as an analogy, and we've got a bigger target atom now, we've got a target atom with a bigger nucleus, then what's going to happen to the likelihood of those electrons getting close enough to the nucleus of the atom to create high energy X-ray photons?
Increase.
It increases. There you go. So, looking at the distribution spectrum for gold, what do you see? We get an increase in numbers. The peak energy remains the same because we hadn't changed kVp yet, we just changed the size of the nucleus. We get an increase in numbers, and look at where the peak of that distribution spectrum is compared to the one directly below it. What do you see? It's slightly to the right. So you get an increase in average, you get an increase in peak or in numbers. So you drop down to tungsten, and then you go down to things that are significantly lower atomic number. And what do you see in their spectra? Something we can't really make sense of compared to this. Everything changes, right? So in your target material, everything changes, with the exception of 2 things. One is the only thing that affects your peak energy is, and the only thing that affects your minimum energy is filtration, right? So you look at the spectra there, and they all come off at the same spot on the left-hand side, and they all end up at the same spot on the right-hand side. But everything in between is different. So what we're gonna focus on are these and not so much changing target material. And the reason for that is the only place you're gonna see a different target is gonna be in mammography. And we're not doing mammography here, so we're gonna focus on tungsten. So these are the things that affect the tungsten distribution curve, the Grimm spectrum, the emission spectrum for Grimm's X-rays. Is as we increase filtration, we lose numbers, we're left with a higher average energy, right? And we get a higher energy level of our minimum energy. As we increase KVP, we increase the peak energy, that's why we call it KVP. We increase the average, so it pushes it towards the high energy side, and we increase the numbers. As we increase mass, the only thing we increase is the numbers. And as we change voltage waveform from single phase to three phase, then what we get is a higher average and an increase in numbers, slight increase in numbers. Okay? So big deal. What does all this mean? We're moving into next semester. What affects your image? That's how we started this. What affects your image? What gives you a crappy image? Fog, right? Fog. So anything that increases fog or increases either the average or the peak energy increases fog, relatively speaking, right? So high KVP, good for the patient, bad for the image because it creates a lot of, because we get an increase in penetration, increase in competence, increase in average, increase in competence, right? So we increase filtration. We increase filtration and we get rid of those low energy photons, but what we're left with is something that's more likely to penetrate through the patient. If it's more likely to penetrate through the patient, it's also more likely to create fog. Right. So good for the patient, not so good for the image, right? In voltage waveform, we go from single phase to three phase, then we get an increase in average. We get an increase in average, we get an increase in what's more likely to penetrate through the patient, so we get an increase in, same answer, fog. So, good for production, right? But not so good for the image. So, mass, though, you know, is just one-to-one thing. As we increase mass, we increase exposure to the patient. That's not good for the patient either, but we've got to have mass as well. Okay? Y'all kind of got all this? That's all brims. Okay? It's all brims. Now we got to do characteristic too. The characteristic conceptually is harder, but as far as the spectrum goes is easier. So how do characteristic X-ray photons come into being?
By knocking out an electron from.
There you go. Now we're there. By knocking out an electron. So we got a nucleus. And I don't want to draw that as an N. That looks like neutral. So we got a nucleus, and then we got electrons, right? 2 in the inner shell, as many as 8 in the outer shell, and that's roughly. That's 6. Okay. There. So what we get is a projectile electron comes in and it knocks one of those out. So as it knocks it out, the electron that is escaping, you know, both of these are going to go off in different directions, potentially. So we've got free radicals, basically. If that was inside of your body, that's what we would call it, but just right now, we're just going to call it a electron. You got a vacancy there that's going to be filled in one of 2 ways. One of these other electrons that are buzzing along may snap into place. Okay? Keep in mind that this may happen, and it's drawn in the textbook, this may happen multiple times by a single electron. So it may bounce around off of a couple of atoms, it may penetrate through a couple of atoms before it actually does this. So some of these are gonna be losing energy as they get close to an empty shell. So it's conceivable that a free-floating electron could snap into place there. And what's gonna happen is we're gonna get an X-ray photon that's created in the energy range that is the difference between the binding energy here and the binding energy here, okay? So tungsten atoms, and that's all we're interested in is because that's what our target's made out of. Tungsten atoms, the inner shell binding energy is 69 keV. KeV and KVP are really pretty much the same thing, equivalent-wise. So this electron has to be coming through with the kinetic energy of at least that in order to eject that, right? If it only has 68 kVp, is it going to knock it out of place? No, it's impossible. Won't do it. It'll bounce off. Now, if it bounces off, is it going to create X-ray photon?
No.
Probably so, because it lost kinetic energy. We don't really, we don't study that for whatever reason, I don't know. But, it's going to create X-ray photon. But it's not going to create a characteristic X-ray photon. Characteristic X-ray photon involves the ejection of an electron and the replacement of another electron. So if I change from 68 to 70 kVp, will it? So that was kinetic energy, that wasn't, KeV. So if we set 70 kVp, my machine's shooting right, and I send these things across with kinetic energy of 70 kVp, it could eject that, right? So that binding energy is 69 kVp. What's the binding energy of this? It's a trick question. Is it bound to anything? No, so the binding energy is zero, right? So if we knock it out with that one and we replace it with that one, then again, mathematically difference means subtraction. 69 minus 0 equals 69 kVp. Okay? Now, how can we change that number? How can we get a characteristic X-ray photon with higher than 69 kVp?
Having an income electron with a different energy.
Incoming electron, so we change that to 100 kVp? Okay, so if 100 kVp hits that and it knocks it out, and then this one comes along and it snaps into place, what was the binding energy of this one? 69. What's the binding energy of this one? 0. So 69 minus 0 is 69. Right. So, does it matter what your KVP is set as long as it's above 69 KVP? Does it matter what KVP you're using, and does that change your characteristic spectrum? No. No. The only thing that's going to change your characteristic spectrum is change the target atom. That's it. The only thing that's going to change characteristic spectrum. Now, if we did the same thing out here, 100 kVp, we knocked that one out, it went off, and it also grabbed a free floating electron. Could we create a characteristic X-ray photon there? Absolutely. Now, what's the L shell binding energy? 12. Very good. Very good. It's 12. We didn't really study that because, for whatever reason, we don't care. We just don't care about anything but the K shell. But the binding energy is 12. So if this one snaps into place, then we're going to create an X-ray photon. And what's the energy level of that X-ray photon? Minus is 12 kVp. Okay? Now, we don't really care about that interaction because 12 kVp, if the average energy of our X-ray beam is 1/3 of the peak energy, then what's the peak energy that we're looking at if that's average?
4.
Well, if this is the average, if 12 kVp is the average, then what's our peak energy?
Oh,
36, right? When's the last time you used 36?
you don't,
Never, right? So, but here's this. If we eject this one, oh, we got another electron. Let's get busy. Let's get rid of some of this. We eject this electron, and then this one snaps down into its place. What's the binding energy here? 12. What's the binding energy here? 69. So this X-ray photon is going to be the difference between these two, which is going to be what? 57 kVp, right. Now, why we don't recognize that in our distribution spectrum, I'll talk about that here in a second. I don't know, I really don't know. But the only one that we're really interested in graphing is 69 kVp. So when you're looking at your distribution spectrum, you're gonna see two things. You're gonna see the brim spectrum, and that's this bubble. And then you're gonna see one thing on going through all of those at the same spot, and it's just gonna be represented by a spike, and that is your characteristic spectrum. Okay? And that should be representative of 69 kVp. Okay? So it's just going to be represented by a spike. It's often referred to as the discrete spectrum. Discrete just meaning, in this context, meaning distinct, right? So it's going to be distinct at 69 kVp all the time. Does that mean that you don't create characteristic X-ray photons in any other energy level? No. If you look on page 128, figure 7-9 represents all the different energy levels you can get off of characteristic X-rays. So you've got 5 above 50 kVp, and then you've got 9 or 10 below 25. So truly the 25 kVp don't matter. Above 50 kVp are really some pretty good X-ray photons. But the only one that we recognize, if you look at figure 7-8, is that spike right there, and that's the highest energy that you can get off a characteristic, and that's 69 kVp. That's distinctive for tungsten. No other atom, if we were to use it as a target, would have the inner shell binding energy and the ability to create an X-ray photon at 69 kVp off of that inner shell electron. So let's do this. Everybody got this? Let's put this over here. So if I were to draw a series of spectra tell me which one has which characteristic. So I'm going to start with a baseline that looks like this. Okay? Then I'm going to draw another one. I'll try to make these representative. That's ugly. Okay. So what could I say about this one? What could give us this screwed up high energy side? Does the low energy side look any different, really significantly? No?
very high KVP.
Okay. What determines your KVP? Or what indicates you have high KVP? The tail on this end, right? Okay. So let's walk through it then. Which one of these has the longest tail on that end?
Third.
Huh?
The third one.
Well, that's just part of the graph.
Okay.
The bottom,
Yeah, bottom.
right? The bottom tell me about the bottom.
It's higher left,
Hmm?
it's going to the left,
Going to the left,
maybe,
this portion here?
yeah.
Yeah, if I were to
If you-
draw it in context with the rest of them, maybe it should look more like that right there. So we got a higher average. What else can you tell me? What does it have that nothing else, no other one has?
The characteristics.
Characteristic spike. So that one tells you that your KVP is where?
69.
At least 69 or above. The rest of them are not, right? So this one has, what does this represent?
The
The average. So we're at like 12 phase here, right? Because we got a very high average. Our peak's not very high, but we got a very high average, and our minimum is about the same. What I should have done is maybe another one that comes off here. What would that one indicate? Here to here. What changes this portion? Filtration, right? So we've got a little filtration, a lot of filtration. A lot of filtration on this one. Okay? So anytime you see a distribution curve that does not have a spike on it, you gotta come to one conclusion. If it doesn't have any numbers on it, you gotta come to one conclusion, and that is that your KVP is below 69, right? So if you've got this long lead-in before you start to get to your distribution curve, what does that tell you? Yeah, you got a lot of filtration. If you're comparing two and the tail on the right-hand end is longer than the tail on the left-hand end, what does that tell you? Higher KVP, right? If you got a higher average, but your lead-in time here is the same between two, then what you've got to have there is single phase versus three phase or high frequency. Okay? So if again you're looking at two of them and one of them looks like that and the other one looks like this, peak energy remains the same, average should really kind of be in the same area, minimum is the same, then what's the difference between those two curves? Mass only. Right. So again, why does it matter? Decrease in contrast, decrease in contrast, increase in exposure or density, right? Increase in KVP, decrease in contrast. Y'all been through contrast and density, right? Contrast and exposure. And then, what do we say on this one? I think this was supposed to be an increase in KVP over these, but less than that one. So increase in KVP, decreases contrast. Increase in mass, increases exposure. Increases in filtration, decrease exposure, so decreases density, changes your index number, but decreases contrast. And change from single phase to three phase increases your exposure, decreases your contrast. Okay? So let's see if I missed anything. Yeah, some of this stuff, you know this stuff. Most of what we create is heat, 99% heat, 1% X-rays. Characteristic X-rays involve the removal of electrons, and it accounts for about 15% of your beam, whereas brims just loss of energy because it's slowing down. And that is 85% of your beam. That's really pretty much it.
What's the only thing that changes the characteristic spectrum?
KVP. Or, I'm sorry, the only thing that changes the characteristic spectrum is your target material. KVP determines whether or not you get a characteristic spectrum. Right? Because if you're below 69 KVP, no characteristic spectrum. If you're above 69 KVP, you will. So really the density and contrast information that I kind of wrap this up with is kind of an intro into next semester. If you struggled in intro this semester, I really recommend that, I've posted some videos from last year whenever Corona first started off, and we had to go to online. They're kind of rough, I'd never done this before, and sometimes I was teaching to an empty classroom, and that's kind of weird, So they don't start at the start of the semester, but what we're going to start with next semester is a review of this semester. So we're going to run through 5 through a little bit in 9 for the first test for next semester, and then we're going to pick up with chapter 13. So we'll talk about chapter 13, then we'll back up to chapter 10 and run through 10 and 11 in the semester with some digital and computer radiography. But if you struggled in intro this semester, really kind of recommend maybe, if you get some time and you just pour it out of your mind and you miss me, you can view the videos. I think the videos actually start in chapter 10. And when when it hit, the technology was such that any video, we're supposed to have everything that we post captioned. And the technology allowed us to automatically caption anything that was under 8 minutes. So what I had to do was record this big long lecture, and then I had to cut it up into 7 or 8 minute blocks, and then click a caption button and let it run through the captioning. So a lot of those videos are very, very short, and that's why I kind of cut up. But again, if you struggled, it might be helpful for you to review some of those, or to look at some of those, or review your intro notes before we get into next semester. Because we're going to hit this and what Trina talked about in the intro this semester really hard next semester. We'll cover it 3 more times. We'll cover it next semester in depth, and then in your sophomore year we'll cover it twice. It ain't going away. This is one of the biggest portions. Imaging is one of the biggest portions of the registry. It's the only portion that we can, because it's complicated, is the only portion of the registry we cover 4 times repetitively with no real difference in them throughout the curriculum. We cover positioning in 3 different semesters, but it's different every time. Imaging is the only thing that we cover the same, essentially the same 4 different times. It's complicated. So really recommend that, again, if it was tough for you, it ain't gonna be any better next semester. Okay? So, final one Friday, 8:30. Yep.
On the last sentence of the review, it says identification from a step wedge image, the X-ray with higher KVP.
Yeah, higher KVP, again, on that step wedge talked about before, would be if you penetrate this step, if you're comparing 2 images and you've got penetration, clear penetration through this step, that would be higher KVP than just penetration. So the more levels of gray you see, the higher the KVP.